topic now we are going to take up is transistor load line analysis. Okay. We're also going to talk about something which we call as the operating point. So both these can be done for the input characteristics and the output characteristics. Okay, but then we are just going to do it for the output characteristics now. Okay, I'm just going to take one, and I think you can easily do it. So the circuit will more or less remain the same. Okay, let me just quickly draw the circuit again. Okay, I'll also suggest all of you to not just refer to the old circuit and try to understand. If you keep on drawing the circuit again and again, probably this is going to help you much better. Okay, because you know practice is very important. So I'll just that's why I also prefer drawing it so that you can just have a look and then see if it's a normal class you would have drawn it. I'm hoping that you are doing it. Okay, so that's important. So if you're using a pen and a paper, I think it will be much more faster with the way I'm doing it. Okay. Just keep less number of cells. You can give more number of cells. Okay, no issues with that. So we're just going to take the same NPN transistor and we are going to just analyze it. Okay, so probably I can just use the pen now last. So whenever you draw this circuit, okay, it's important that you basically yes, so you can always begin with the transistor, okay, drawing the transistor, drawing the arrow, and then you can begin drawing the different parts. That will always help. Okay, so this side we are going to have our signal. Okay, so suppose if it's an amplifier, we are going to have a AC signal, AC current, or the voltage. But then for this particular part where we are going to analyze the load, okay, load line, we are not going to have any signal. So we'll just not put any kind of signal here. So I'll just clearly write it, no signal. So I don't have any kind of input signal as of now. Okay, but then the other parts are there. Okay, I'm not doing any kind of amplification. That is exactly what I mean by no signal. Okay? So we have got IB here, and we have got the emitter current here. Okay, we have got the collector current here. Okay, and then whatever measurement we are going to do, we are going to do it across the load. So the reason for calling it a load line is because we have got a load connected at the external end. Okay, so we can just write it down as RL or RC. Okay, both should work. And then we have got VCC here. Okay, and then we have got VBB here. Okay, so let's just keep the notations same. Okay, so that no one gets confused here. Okay, and what I will do now is I'm going to just use the circuit diagram. Okay, to actually and use Ohm's law to actually write down the equation. So what I will do is this: we are going to take this, and this is nothing but VCE. Okay, so this is the voltage across the output. So what I can do now is I can use Kirchhoff's voltage law in the output circuit. Okay, so what we will do is we'll use using Kirchhoff's voltage law in the output. So if you just look into the circuit, this is your input and this is your output. So the output loop we can actually consider to write down the Kirchhoff's voltage law, right? So you can just see that we basically have a voltage drop of VCE across the collector and emitter junction, and we are just considering it in the common emitter configuration. Okay, so that's why yesterday I have done common emitter configuration, because I wanted to explain load line and everything in terms of common emitter configuration. I also told you that common emitter configuration is one of the most widely explored configuration of transistor, although you can have common base, common collector, and common emitter. Okay, so you see that the voltage here is VCC. So across the output circuit, the voltage is VCC. Okay, and the voltage drop will occur across RL, right? And you have the current, which is actually IC, which is actually flowing in the circuit. Okay, so basically you have it as IC. So we'll just take it to be IC into RL. So if we just use the Kirchhoff's law, we are going to basically have it, okay? And please remember, we are not applying any kind of input signal as such, okay? We're just consider this IC, okay? This is the current that flows across RL, okay? So if we have this particular current, so we can just take IC into RL, and then this will give you the voltage drop across the resistance RL, okay? That's the load resistance. So this is the equation that we have, okay? That we can just write down this equation, okay? And now what we are going to do is, we're just going to draw the characteristic curve, okay? So let's just draw the characteristic curve here. So from here we are actually going to get what we call as the load line, okay? So this part is IC, okay? So we are just writing down the output characteristics, okay? So we're just going to write down this as IC, and this IC is in milliamps, you know, already know about it, okay? And then this is VCE, and this is in volts, right? And then we have seen in yesterday also that if we're actually going to draw the output characteristics, we are going to get these kind of curves, okay? We are going to see that the output current will actually more or less remain constant. So I hope I'm drawing it okay for you to just be sure that this is clear. And then, you know, this basically depends on the base volt current. Let's say this is IB. Let's say I'll take it as 5 microamps. Whenever you are drawing any kind of circuit diagram, okay, I'd always suggest you to keep it complete. Okay, that's very important. Let's say this is 10 microamps, and let's say this is 15 microamps. So depending on the input base current, you are going to get this particular output characteristic curve. Okay, so this is 0. Okay, now let's just use this equation. Okay, let's just use this equation. So I just need some more space here, and you can actually do two things here. Okay, so let's just do the first part. So you are basically going to find out two coordinates here. What are those two coordinates for which you need the load line? Okay, just listen to this first, and then you'll understand. First coordinate is 0 on the x-axis, and let's see what happens on the y-axis. We don't know. And the second coordinate would be 0 on the y-axis, and there will be some value on the x-axis. How do we find it out? We find it out using this particular relation which we got. Okay, so you see 0 on the x-axis. So this is your x-axis, this is your y-axis. Okay, so 0 on the x-axis. Okay, that means we are going to talk about somewhere here. This is the 0 on the x-axis, right? So if we say 0 on the x-axis it's IC. So what we can do is we can put IC is equal to 0. Okay, so when IC is equal to 0, equation 1 will imply, please concentrate on this. If this is 0, VCE is VCC, right? So we'll get that as VCE is equal to VCC. Okay. So let's just have a look at this now. Okay. So that means this would be 0. Okay. And then this would be VC. Okay. Sorry. Just wait. I think I just mixed it up here. IC is equal to 0. I get VC is equal to VCC. Okay, let me just take the other part now first. When on this part you see VCE is equal to 0, we can take. Okay, so if we take VCE is equal to 0, one will imply that VCC is equal to IC into RL. Okay, but then on the y-axis it's IC. Okay, so IC can be written as VCC divided by RL. Okay, so one part we have got VCE is equal to VCC. So let's say this is some point here, and the other part we have got IC is equal to VCC by RL. So we can say it is here, VCC divided by RL. Okay, so if you look into this particular coordinate system, on the y-axis we have got it as VCC by RL, on the x-axis it is 0. So this is 0, and this is VCC divided by RL. Okay, on this particular coordinate, okay, we have got the x-axis as VCC. So we can just write it down as VCC, and on the y-axis it's 0. Okay, so you've got 2 points here, and this is your VCC. Okay, let's just have a look at it again. We have this relation. We are going to find out 2 points on the y-axis and on the x-axis. Okay, so if we just want to find out exactly a point on the x-axis, y needs to be 0. So this y is 0, and then we need to find out what is the value of x. Okay, so for this what we do is we make IC to be 0. We find out VCE is VCC. So when IC is 0, VCC is equal to VCE. So you can just take this point, and on the other side what we can do is we can just put VCE is equal to 0, because you know this axis is VCE. So VCE is 0 throughout this. Okay, so you can just take this to be VCE is equal to, sorry, IC is there. Okay, so what we do is we put VCE is equal to 0. We can get VCC is equal to IC by RL. So we get the value of what is IC. So IC is VCC by RL. So we have got 2 points on this, and now what I do is I join these 2 points. Okay, if I join these 2 points, this particular point, this line is basically called the load line. Okay, so this is your load line. So we might have some practical question based on which you might be asked to draw the load line, and this is something which we are going to do. Okay, so you know, this is important because what happens is this will actually tell you what is the operating point. Okay, so if you just look into this, let's say you have drawn a number of lines for different base current. Okay, and at some point you are going to get a point here. Okay, so let me just draw it in this way, white line. Okay, this particular point is called the operating point. Okay, so usually when a transistor is used as an amplifier, the aim is that you are actually going to apply an input signal. Let's say this is your input, and the output signal should be, let's say this. Okay, this is an amplified signal. Okay, and you know, energy can neither be created nor destroyed, so energy needs to be supplied to this so that this actually gets that energy and gets amplified. Whenever you're looking into a waveform, we are actually talking about in terms of energy. So this will represent an energy, this will also represent an energy. The point here is that if this is smaller in amplitude, this is larger in amplitude, that means this particular thing has got a larger energy. Where did it get that extra energy from? That extra energy is actually obtained from the biasing that we have, VBB, VCC. Okay, so the energy that this biasing has cannot be infinite. Okay, so the energy conservation still works. Sometimes it does happen that when you're actually going to get an output signal, you'll be getting some kind of clipping. So probably this portion won't be there. This will be clipped and this will be clipped. So you are not getting a full signal. Okay, the signal that you get might be like this. You'll be getting like this, and then this, and this, and then this. Then the signal gets clipped. Okay, so that means there has to be an optimum voltage VCE. Okay, and the optimum current IC at which we should be getting able to get the full signal, the full signal. And that full signal can be obtained if the device is working at this particular operating point. For example, any device will have an optimum condition, and this might be a good optimum condition. I might be having the base current at 10 microampere, and that base current I'm going to get this much of VCE, and this is my IC. Okay, and that is why finding out the load line and then calculating the operating point is very important. Okay, so we'll just look into an example and try to understand it better. Okay, but then for now I think this entire slide gives you all the information what you need for a transistor load line and operating point. Okay, and this is actually very important. So let's take it this side. Yeah, so I think this is all clear here. What we do usually is the question might be analyze a transistor load line in CE configuration. So what you usually do is usually draw this circuit, and then you can simply write down using KVL in the output. You can draw this, and I will always suggest you to just mention what are the terms here. Mostly you just write down IB, IE and IC are the base collector and emitter current, okay? And we have got RL as the load resistant connected across the output, and VBB and VCC are the input and the output biasing, okay? So you can just mention that part. I think that much is okay. You can draw the circuit diagram. When you draw the circuit diagram properly, you can, if it's a 5 marks question, 2 marks actually itself is with the circuit diagram. So draw it properly, and then just write down what is the KVL, and then just do it, okay? And then you write down output characteristics. So you can just mention the output characteristics is the curve between the output current, collector current, and the collector emitter voltage, okay? So once you draw this, you're basically going to get these curves, okay? And then you're actually going for the load line, okay? So for load line, you have to basically find out 2 points, one on the x-axis, one on the y-axis, okay? So accordingly, you make the content 0. So for this particular point where you need VCC, okay, you can just make IC 0. So when you put IC 0, you get VCE is equal to VCC. So that is 1 point. And for the other part, you can just make VCE 0 because this is VCE versus IC. Put VCE 0, you find out what is IC. So IC VCC by RL. So dimensionally also this is correct. This is basically current V by R. This is also dimensionally correct because this is also voltage, and on the x-axis we are also plotting voltage. Okay. So this is what is load line is all about. Okay, and this is important. And probably we can just do one numerical on this so that we understand it better. Okay. So in the next page, let me just write a numerical for you. Okay. So what we are going to do is sometimes some values and circuit diagrams will be given, and based on this, you have to basically draw the DC load line. So we are just concentrating on the DC load line. Okay. So the typical question might be for the circuit shown. Okay. Draw the DC load line. DC load line. What I'm going to do is I'm just going to draw a circuit and probably delete this page. So this is the question that you have. Okay, draw the DC load line for the circuit. Draw the It's not that you need to draw it up to scale. That's fine. If you just find out the values and just plot it as a graph. Okay, that's all. Okay. So let me give you just 10 minutes, probably 5-10 minutes, so that you can just look into the previous problem or the previous solution that I've given, okay, or the discussion that we have done on the DC load line, and find out the values on the x-axis and the y-axis. I think you've already done it, okay, but I think it's very simple. So what we usually do is, I think whenever you're going to look into the DC load line, just do these steps, okay. First put IC is equal to 0. When you put IC is equal to 0, you get VCE is equal to VCC, right? And VCC, the value is already given to be 12.5 volt, okay. So since the value is already given, okay, and VCC will be here, so this particular point will be 12.5 volt. We're just taking it randomly. We're not just basically scaling it down. Okay, so don't worry about these points. Okay, and for the other part, what you do, you just put VCE is equal to 0. Okay, and then you can actually get what is your IC. Okay, IC is equal to VCC divided by RL, right? We've got RL here. Okay, so this is nothing but VCC. We already have it as 12.5, okay, divided by RL. RL is 2.5. Okay, so this is in kilo ohm, please remember this, and this is in 12.5 volt. Okay, so if you just do the calculation, this is kilo, so it goes up 10 to the power minus 3, and 2.5 into 5 is 12.5, so it is 5 milliamps. So that's current, right? So it will be somewhere here. Let's say this is 5 milliamps. Okay, and then if you want to draw the DC load line, what you're going to do is you're going to just take this, join it here. That's all. So this is your load line. Okay, so this is your load line. So whenever you get these kind of questions, it probably will be just a 2 marks question. Okay, I will give you the circuit, and you are basically just supposed to draw the load line. So it should not be very complicated. Okay. So this was a simple question, should not be complicated. Okay, let me give you another question where we're actually going to talk about the operating point. Okay, so let me take a new page here. Okay, and here I'm not going to just draw the circuit. You can assume the circuit. It's similar. Okay, the circuit is similar, whatever we have done before, or maybe okay, I'll just take another page, I guess. Yeah, I'll just take this page. Yeah, take it here, delete these parts. So we're not going to use it, okay, and then we're going to just write down a separate question altogether. Or maybe I can just write down the question only. I really don't need to draw the circuit because it's quite obvious. Okay, not take time on this. So try this problem now. The first part will be more or less same, okay. In the circuit diagram shown, so you can just consider the previous diagram, okay. In the circuit diagram shown, okay, the first part of the question would be if VCC is given now 12 volt, okay, it's not 12.5, it's 12 volt, and RL, okay, let's say RL, or I'll just write down capital L, is equal to 6 kilo ohm. So whenever you do it, you can always just do it in a way you like, okay. You better draw the circuit diagram and everything else, okay. Draw the DC load line. So use a similar procedure to it, okay. It's very simple. Is another part. What will be the Q point? Q point. So I'll take this question to explain certain concepts. If zero signal base current, if zero signal base current is 20 micro amps, okay, and beta is equal to 50. Okay, that's the question. Now I will give you some time to do it, okay. So probably I'll just make it. Okay. So this is VCC, this is RL, okay, this is 6 kilo ohm, okay. Then you have to draw the DC load line. What will be the Q part of the zero signal base is 20 microamperes, and beta is equal to 50. Okay, first draw the DC load line, okay, and then I can tell you the idea about zero signal current, okay. So there is zero signal base current. You can also get zero signal collector current, okay. So zero signal collector current will be IC. So if you have the base current and if you know the value of beta, you can find out what is the collector current, okay. Based on that, you can actually find out what is the operating point. So let me outline.
2 milliamp.
Okay, that's IC. And what about VCC? 12 volt, right? Because that will basically remain the same. So it's actually easy on this part if VCE is already given, right? So you're getting 2 milliamps. So everyone should be getting 2 milliamps. Please check. Okay, and use the same equation, the Ohm's law, the KVL equation. Okay, and on this side you should be getting around 12 volt. Okay, so please check, all of you should get that. Okay, so once we get this, we are actually going to get the load line. So we have the load line now. Okay, so the first part of the question is done. The second part of the question actually asks you what will be the Q point if zero signal base current is 20 microamps and beta is 50. So I told you that within the load line somewhere you are going to get the Q value. You're going to get this Q. So you're basically going to find out which is that particular operating point. Okay. For finding out that particular operating point, you usually need what is the value here. Okay, that means some value of IC you should be having, some current you should be having. So you need to find out that IC, and corresponding to that IC, you can easily calculate what is your V, okay, or VCE. Okay, so I think this is simple because if you just talk about it in technical terms, it is called zero signal collector current. Okay, and you know already the relation between collector current and base current and the amplification factor beta. Okay, so it is basically called zero signal collector current. Okay, collector current. Okay, so zero signal collector current is basically called IC. There is no clipping. You are getting a good signal at that particular point, and beta is equal to nothing but IC divided by IB when we look into it from a common emitter perspective. Okay, so beta IC is equal to beta into IB. So you can always refer to the previous lectures, and there you'll actually get this. Okay, IB. Okay, so beta is 50. That's just a factor, and then we have got IB, which is 20 microamps. Okay, so if we just do this calculation, okay, uh, or probably we can just do it this way, since we are talking only about milli. Okay, so you can just simply write it down as 20 microamps. Okay, if you write it down in milliamps, you have to just divide it by 10 to the power 3, so it is 0.2 milliamp. Better to write it in milliamps because we are doing it in milliamps on the y-axis, so it is 20 milliamps. Okay, so what you get if you do this is 1 milliamp. 1 milliamp. So what we have here is 1 milliamps. Okay, and then if this is 1 milliamp, you can easily find out what is your VCE, right? So we can just do it this way. VCE, this relation will more or less remain the same. VCC minus IC into RL, right? So this is VCC. VCC we already have it as 12. Okay, VCC is equal to VCE is 12 minus IC, we got it as 1 milliamp. Okay, into 6. Okay, so if we just do it in this way, I think I should not make you confused with the units here. Please be very clear. This is in volts because this unit is in volts, right? So this is in volts. Okay, this is 1 milliamps into RL. So RL is already given to be 6 kilo. So 6 kilo ohm. So kilo is 10 to the power 3, milli is 10 to the power minus 3. Okay, so you basically have it out. Okay, cancelled. 10 to the power minus 3 to 10 to the power 3. So simply this result will be nothing but in ampere and ohm. So that means this is going to be volt, right? So this is going to be simply 12 volt minus 6 volt, which is 6 volt, right? So that means this value is going to be 6 volt. So this particular point is going to be 1. Sorry, it's x-axis first. 6, comma 1. That's all. That's the operating point. Okay. So the operating point, if you write it down in simple words, okay, operating point is 6 volt 1 milliamp, and this completes your answer. Okay, so it's basically, let's say, 4 marks. Okay, first part 2 marks, second part 2 marks. So if you know it, it's simple. If you don't know it, then you should say, okay, it deserves around 20 marks, 30 marks. Okay, but then you know the concept, so I think it should not be very difficult. Okay, so this is where we stop with the first part. Okay, where we talked about the DC load line.